Okay, thank you. Let's try to investigate that. This is the pointer. And this move the slide. Perfect. Is it working? Yeah. Okay. Okay. As in the title, this is try to wrap Geant4 in Julia. Okay, as you know, okay, Julia is a priori good language for high energy physics, and one of the essential things that we need to evaluate for each adoption in our domain is how interoperate with existing C++ libraries. I think this is essential because we are not going to write everything from day zero. Okay, that's clear. So an excellent playground for this kind of evaluation, I thought that would be Geant4 because it's large, it's complex, and probably it's not going to be rewritten immediately. So, and also at the same time, because there are many users of Geant4, it could, okay, the result of the exercise could be a nice to have new functionality to Geant4 that can be used by some people. Okay, I don't think I need to introduce you what is Geant4 in this community. It's a toolkit for simulation of passage of particles, elementary particles through matter. It's open license. It's over 2 million lines of code and has been developed for about 25 years. Okay, and is mainly used in high energy physics, nuclear physics, medical, space, and okay, on high energy physics in particular, I think it's 99% of the experiments use Geant4. Okay, it's really very well in every experiment basically. Okay, the first step you need to do is to generate the wrappers, and similarly to Python, to call a C++ from Julia, you need to write or better generate this wrapper, this single line basically for each of the methods that you want to publish into the Julia, you want to offer to Julia. And for that I use cxxwrap.gl. And then you need to write this small code for each of the class as Philippe mentioned already, and for each method. This is very similar to other bindings to Python, okay? This PyBind 11 or originally the Bush Python, I don't think now is very much in use. Okay, thanks to the package developed by Philippe, Rapid, which makes use of the LLVM libraries to generate these wrappers automatically, and really is a lot of effort that you save in there, okay? Because otherwise it's really very tedious. And also at the same time, if there is changes if you want to track the evolution of Geant4 with new versions and things like that, you just turn the handle and eventually it will just work. Okay, now once you generate the wrappers, the basic interface is rather straightforward. The only difference you have to convert the thinking of C++ into the thinking of Julia. In Julia, you don't have classes, you only have structs. And then you don't have a real inheritance, you don't have methods. But okay, once you adapt to that, then it's quite straightforward. One advantage of Geant4 is that since all the classes are prefixed with G4, you can export automatically all these new types into Julia. You will not have a clash. Okay, that is really. Otherwise, you will have in other kind of packages you will have to put Geant4 dot something to otherwise you will have typically you will have clashes because there are many classes that are similar in all these package domains. But okay, there is some specialities there that some Geant4, as I said, is 25 years ago, and at the beginning they were inventing their own types for things that then appear more commonly on the standard library and things like that. And you have things like G4 string, okay, which is nothing else than a std string. But okay, but when you call, for instance, in this example I have here get version string from the run manager to just instantiate it, what you get is it's a G4 string, which is wrapped. In Julia is represented like this. You have a pointer, but then you have to basically convert that into a string to get. But there is a little some things like that. Okay, not many, but that sometimes you need to finalize the conversion. Okay, now I can the thing is trivial using Geant4, and you just have everything, and you just instantiate the classes that you want, and that's quite straightforward. How this is implemented at the level of packages. I wanted to have the Geant4 package that you're using here a purely Julia package. So everything else that is binary, is in a binary package. And at the same time, I wanted to separate what is the wrappers, what is the dynamic library that you need to produce with the wrappers. I wanted to separate from the real normal libraries of Geant4 package. Okay, so that the distinction is clear there. And this is great because there is all this binary builder, all these things that Mose was telling us, I think on Monday, which helps really enormously on this exercise. Okay, you can produce this Geant4_GLL, which depends already on things that exist in the binary repository, and that contains all the libraries, and it contains also the data files. Okay, perhaps the suggestion was perhaps we need to separate the data files and just to make it a bit more flexible, because it is true that new minor versions or patch versions of Geant4 will not change the data files. So if you have it separate, you will have less things to download, because you will reuse the artifacts that you have already downloaded. And then, okay, that's the library that you built, the wrapper, and that obviously has a dependency on CXX wrap, which is what you use from Geant4 here. Okay, that's quite a slate. Now, once we have that, then I thought, why not to give it a different, more user-friendly interface to Geant4. Okay, I don't know how many of you have already done some development using Geant4, but it's a rather complicated way of going. Okay, and now the reason is very simple. I try to summarize it here in this graph. But what you have is the Geant4 engine, is where you have all the geometry description, the models, the processors, and so on and so forth. And you as a user of this toolkit, you have to provide a number of inputs for your things that you want to simulate, and this will produce some data for you. So the inputs, typically, you need to tell the Geant4 what is the geometry. Okay, you need to tell either by providing code. You write C++ to provide the code, or either by provide the GDML file, an XML file that describes the geometry. Then you need to provide what is the magnetic field you want to use. Okay, either again, perhaps using some of the standardized magnetic field, uniform magnetic field, or provide some customer specific magnetic field that you have mapped on your detector, or you have done. You have to provide the physics that you want the Geant4 to produce, and here you make a menu of the different for each particles and ranges and energies. You combine the things that you want. You need to provide also what particles are your primary particles in there. Okay, again, you can use the predefined particle gun, which is a single particle, single energy, or you can build something that is what really your sources of particles that you want to just exercise. Then, of course, you configure the engine with the more parameters and your commands. There is all sophisticated user interface commands that you can configure all this engine. And the way you extract the information of Geant4 is by providing what they call user actions at a given moment during the evolution of this tracking these particles through the matter. Every step, there will be a function that if you have provided, a user function that will be called, or every time you start a new particle, a new function will be called, and so on and so forth. When you start, when you end, and so on and so forth. These are what this technical call user actions. Another alternative is that on a given detector, or given detector, you say every time a particle enters that detector, I want to get informed, okay? And you provide, again, functions there that will tell you when something happens on that detector, and that you can extract the information you want. Or something more already cooked is that you define meshes and say, look, give me the energy deposit in this grid, okay, or those on this grid that you define in different geometries. And this is in here there is less user code that you have to write, okay? This is basically most of the applications is for medical applications and things like that, that they are not too much interested in writing code, that you just want to have what is the dose on my phantom I receive here, okay? And then the rest, from all these things, you produce data on different forms. It can be counters, can be histograms, can be anything. And then eventually you analyze that or you visualize that. That's basically the overall interface of the thing. And the idea here was, can we do that a bit simple, okay? Because today, the way this is done is basically by providing C++ classes that you have to inherit from some base class and so on and so forth. So the idea is to think about that and to see if we could do something minimalistic, in the sense that the user only needs to define what is really strictly necessary, and the rest will be done by the toolkit, and do it also at the right time, because Geant4 is very sensitive on the moment that you do things. Okay, you can it looks very stupid, but you cannot get a particle property before you have defined the physics and things like that. Okay, if you ask what is the mass of the electron, you cannot even ask. You have not initialized the thing. So it's the order plays really a very important thing. Now you want to obviously to be interactive, because it's an easy way to develop things using a REPL or using a notebook. And you want to make multi-threading in a more transparent, because today Geant4 supports multi-threading, but again, there is a lot of work to be dumped to the user that has to do things in certain ways in order to use the multi-threading. And of course, if you are in a Julia environment, you want to have this easy integration with the analysis and analysis tools that you can have there. So basically, the key point there is the callbacks, because the custom code that you put on this package is always as callbacks. Okay, it's Geant4 that calls your code, and this is happening by inheriting from some base class. Okay, that there are some virtual functions, and it's up to the user to implement these virtual functions. Of course, this doesn't match on the Julia case, but Julia can, especially the CXX wrap can call from C++. You can call Julia, but in this case, what I had to do is I had to provide a basic C++ class that inherits from what Geant4 tells me that I should inherit. In that particular case, I have to. This is for the stepping. I have to inherit from the user stepping action, and the function that will be called all the time is this user stepping action, and that I will forward that into some Julia function, okay? And you have to make sure that here of course you get the arguments the arguments that the Geant4 is providing to you correctly in the G4 step. In addition, because I want that this function becomes like closures, I want also to provide the context to this, the state to these functions, and that's why I am adding here a reference in that particular case to the overall application. So I don't have to have globals anywhere. When this function step action is called, you get what Geant4 tells you in addition the full environment. So if I need to know, I don't know, something on the geometry, from that reference there, I can get geometry information. If I need to know what is the, I don't know, the material of there or what is something else, I can get it. And I need to fill some, if I need to fill some data as a result of this stepping action, I can also get where I should put this data, okay, if it's an histogram or whatever. So I use all that. This is great on CXX wrap. The only difficulty there was that the native closures was not supported on the ARM architecture. And that was a bit of a surprise because I had done all that. And then somebody tried it on the Mac, on the new Mac. I was having an old Mac, and for me it was perfectly working, but on the new Mac didn't work. Okay, and the error was okay. It was not supported. So I had to develop a workaround, but it's okay. Once it's done, it's done. Yeah, the only little pending issue is that because there is this boxing and unboxing of some of these Julia objects there. There is a little number of bytes that are called every callback. Okay, so something that to be look at it. Okay, that's the basic structure, and this is used basically on all these first diagram I showed the interface basically everywhere. The sensitive detector is the same thing. Okay, is that you provide some data structure, your own data structure. You provide three methods: initialize, end event, process hits. This is the three methods that you need in order to implement this sensitive detector. And they basically, you bundle the things together, the three methods and the data structure that you define. And this is what is a sensitive detector that you give it to Geant4. Now, multi-threading, this is another aspect I wanted to offer there in an easy way. As I said, Geant4 comes with it. It's a trivial parallelization. I mean, every thread simulates one event, and you get very good scaling to hundreds of cores and things like that. That's very nice. But okay, but it's Geant4 that manages the threads. Okay. Now, and thanks to the latest version of Julia 1.9, now it's possible to adopt C++ threads from Julia. Okay, and that was really an essential thing there. The only thing that I had to do a bit more careful is the interaction with the garbage collection. Okay, because if you are not careful, Geant4 starts these threads. And then they put them asleep until you start to run, okay? But they are there, and they have been initialized into Julia. And then when the garbage collection starts, they want to know if they are in a safe state, but they are sleeping, okay? These threads. So there was a bit of deadlock situation. Then you have to work around with a bit of gymnastics of that safe enter, leave, safe leave, and so on and so forth. And that is now it's really running nicely. Now the only thing is that user code, which is these user actions and sensitive detectors and so on and so forth, obviously they will run in different threads. But then, yes, you need to put this into the user and make sure that there is no. The user does the correct thing, okay? There is no race conditions there and things like that and some protection. Typically, what is done, which is trivial, and it probably works 95% of the time, is that you clone the data n times, okay, and then each of the threads modifies his own copy of the data, and then at the end you sum the data back. Okay, that's what is done here. But again, if you want to really share some shared data between the threads, you will have to make sure that that you do it correctly. No, the geometry, once is declared and all that, is handled by Geant4. You don't see it. It's data that counters. I mean, I want to count how many steps I'm doing, or what is my distribution of energy deposition, histograms. Okay, so this data that I produce, I have to make sure that because there will be these stepping actions, they will be called at the same time by different threads. Now, how this is done? For here, I give you an example on the user action. This a couple of examples. This is the begin event. Typically, the begin event. This is a function, Julia function will probably initialize something. Okay, they will probably fill some vectors with zeros or something like that, because it's the begin event, and then for every step action, perhaps for this information that you have there, you navigate. Okay, you get from the step, you get the pre-point, physical volume, logical volume, detector, blah blah. Okay, you just fill the things that you want. But the important thing here is that this thing, the data gets sim data. This gets your own thread local copy of the simulation data, so you can freely work on this data. It only belongs to this thread. Okay, so you don't need to worry about the other ones. Yeah, as I was mentioning at the beginning, you need to enter the geometry description, and this is fine. This is it could be done better, but for the time being on this version, I just you call the Geant4 functions to enter the geometry. Okay, typically you create a solid, a box, you create a logical volume, you place it, and then you build the geometry in this way. Or you, as I mentioned, you can use GDML files to read the thing. The only difference between this and what the Geant4 natively does is that you can associate a user structure where you can keep basically the fundamental parameters of the geometry, okay, the parameters, and then you can use this structure to navigate and fill the things. So at the end of the day, this is what summarizes your detector. Now, for instance, this is particular case on this example, I was using how many absorbers and how many layers I have, what is the thickness, and so on and so forth. Okay, that you specify and base this, you can build your detector. Magnetic field, exactly the same thing, the same idea. You have a function that will be called by Geant4, a callback, but you can have an associated structure where it defines the parameters that you want. In this particular case, is a trivial case because my parameters is basically a uniform magnetic field, is a fixed magnetic field. So it's a trivial thing. And the function that will be called by Geant4, the only thing it does, this is the arguments you get, and you just assign the constant magnetic field into the argument that are given there. And again, you define the same thing. You define the data part and you define the methods. So, and exactly the same thing. I mean, there's the same pattern everywhere. Exactly the same thing for the primary particle generator. A set of parameters. For instance, in that particular case, I'm using, for instance, a medical beam, which will have some spread on some angles, okay, that you want to shoot particles. And then this is the parameters. What is the energy? What is the spread on these planes, and so on and so forth. And then this is the function. This is the function that you provide, Julia function that you provide to initialize a thing and to generate for every event. You generate based on the parameters. You generate what you want to have there. Now, once this is done, all this the input, what you obtain is the simulation data, and this again is a user-defined structure where you define what you want the outcome of the simulation to be. Okay, in that particular case, or I put here as an example, this is I want to see the number of charged steps, the number of neutral steps, the number. Some distributions of energy deposition, some histograms, and so on and so forth. So I define my own instruction, and this is trivial. This is really in Julia. There is nothing else to be done. Okay, pam 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 pam. You define your structure, and then on the actions, you just fill this structure with the data that you have obtained from the simulation. The only thing is that if you want to use multi-threaded, you have to provide yourself an add function with this data structure, okay? That you need to know how to add, because each of the threads will be filling this structure independently. You need to know that these are counters, so I add them like this. These are histograms. I add them the same way, okay? Okay, so basically, perhaps you could even do better, okay? You could really do some introspection and find out which of these data members, which of these fields has the plus equal operator has defined, but okay, it's so trivial that it doesn't even make sense. Okay, and once you have all these pieces, you put things together, okay? And this is what I call here G4GL application, that basically it's really everything that I have defined. I have defined my detector structure. I have defined what physics I want, what particle generator I want, how many threads I want, if I want, I don't know, an event, anti-event action. If I want to have sensitive detectors, I do the mapping. This is my sensitive detector I define. This is the logical volume name I want to associate to it, and you just describe that. You do some initialization, configuration initialization, and you just run for a number of events there. If you don't specify number of threads, obviously it will be serial. If you specify the number of threads different from 0, it's multi-threaded. Now, in order to that's trivial. In order to debug, mainly the point is, in order to debug your geometry and your physics, if you are shooting in the right place, or the particle generator is shooting to the detector or is shooting somewhere else, it's visualization is really very convenient. And currently on the package there is some visualization done using the Mackie package that was also presented already in this workshop. The only tricky, I mean, this is quite straightforward, okay? Any of them, of the Geant4 solids, you can represent it easily with Mackie, okay? You just need to produce the mesh out of that, and you just provide a couple of functions, and automatically you get it, the visualization. It's not a big deal. The only tricky part was the Boolean solids, okay? Because it's not obvious when you to visualize the subtraction of two solids or the union of two solids. You know, to create the mesh is a sophisticated mathematical problem. So in that particular case, I use another package, which I now have forgotten the name, which is a C++ package that, again, there was already, the binaries were already, I had to update the version, but it was already on the repository, and I could make use of this C++ package to create out of two meshes, to create the Boolean operation of the two meshes, okay? And I tell you, this is not a trivial trivial thing. But okay, it's there, it works. Of course, perhaps it's not very performant, but I said this is mainly for debugging purposes. Okay, it's not really, doesn't need to be. And then you also, as a user, you can provide things when you do the stepping actions, and you can collect data and you can plot it. Everything is there. Okay, you can plot it the way you want it, and things like that. I put here a few examples. For instance, this is an example I have on a kind of a bubble chamber. Okay, then you can say, I want to draw the neutrals as a dash and the other non-neutrals as solid, and I want to put labels and so on and so forth. You do what you want. Okay, it's quite easy. So that's basically a complete example. Just to give you, okay, you will have, it's the same thing I showed before. You will have a bit more user actions here, okay? Functions, Julia functions that will be called there. Nothing special. Yeah, and that particular example, I'm using the histogram package of Jerry. Okay, that's you can see it. You can see it here. Although this hist1diff64 is an alias of a long thing, but okay, it's there and it works, and it's nice. Yeah, and then you run this example, and this example as I said, it was producing the histograms, and then you have a little plot function with the data that you produce, and this is what you get, okay, in that particular case. Now, I mentioned interactivity, but that's for you is something that is obvious there. You see the REPL. You can play with all the functions of Geant4. Even for debugging, Geant4 is convenient because you can really go to the low-level stuff. Okay, I create a box, and now I want to find out the distance of a given point into the box, and you can really play. You can play on the REPL with something that was not there at all on Geant4. Okay, and also you can obviously that you can have notebooks. You can play with the drawing of the geometry if you don't know all these parameters, what they are and how they look like, and so on and so forth. And it's okay. I generate all that then for the documentation. Now, one word on performance. The performance should be equivalent to C++. It should not be. The only thing I use here a very basic example. Of course, if I do a simulation of one event, Julia, there is an overhead there. Okay, that we know. But then the rest, if you look for many events, this almost disappears and is typically the same. And if you go even multi-threaded, more or less, okay, plus minus 5% is what you would expect there. Yeah, then okay, I have added more realistic examples. There is a number of, on the package, there is a number of things. Water phantom, this is more for medical applications. This is a bubble chamber, it was fun to do. Something to do with the optical photons and customized physics list, that could be also interesting. And then a bit more realistic one is this thing of Atlas style cal test beam that I converted something in C++ into Julia. Just to give you some, it's more complete because the user actions are real signal processing kind of thing that you typically do. Okay, and then plotting the results. This example in C++ is about 300 lines of code, and Julia is 1,000. And yeah, in the time, it's much faster in Julia than in C++. Okay, and the reason I get the Geant4 part cannot be because it's the same. It's only this all this signal processing and all that is done more efficiently probably in Julia than in Python. I've done in C++. Then also I compared it with other bindings of Geant4. It exists a couple of flavors of Python bindings. And then I evaluated the things with some criteria. Okay, and this is a summary. I perhaps a bit biased. Okay, of, of the criteria, but okay, this is a reference, the C++. As you know, the problem is that this installation PyBind the thing is very good. Okay, pip install blah blah is the same as Julia. The friendliness of the interface. This imitates very much the C++ interface. So it gets the same thing. Okay, you have to inherit from a Python class and see. It's not really okay. The Julia I consider it is good. The interactivity both are very good, Julia and Python. Now the running speed, the Python is bad, and it's bad because all the user actions and all that will be in Python. So if you do a lot of things in the user actions, you will have a penalty there. The empty support for PyBind is very bad. Does not exist because of the single the single lock. The lock interpreter lock, and then the Julia. This is very good because it hides. Very good respect to that because it hides most of what the user has to do. And on visualization and analysis, this is there is something in there, but it's very limited. Okay, and in Julia and Python it's good. Okay, just to conclude, the first conclusion is that the CXX wrap works nicely and scales relatively well. Okay, it manages all these things of pointers, cons pointers, cons reference point, whatever. Okay, all this something that you have to. The binary builder is really very powerful to streamline the installation and deployment of these C++ projects. And Geant4 GL is extremely useful as a add-on to the Geant4 projects. In particular, the target thing will be basically for tutorials because it's easy to set up and it's portable, interactive development on notebooks and perhaps on some domains. Okay, and now currently it's still in a prototype state because although it works and you can produce things can, I mean, if people are asking things, perhaps the interface will change, will evolve. So it's not yet a final project, but okay, I think it's very useful already, and it's of course it fully exploits all the tooling of the Julia ecosystem there. Thank you.